Today we're going to be looking at the graphs of quadratic equations. This is the first of 3 days worth of notes that we'll be going through. Might take a few more videos than three, but we'll see what we can get through today. The first thing I want you to notice is this big box on your notes. This, don't get overwhelmed by this. This has got everything that we're going to be dealing with quadratics. So it's something that you can revert back to after we go through all these things individually. I'm going to have you write this down here. Underneath that box, even though we've written it a couple times in our previous notes, that the standard form, and it's even in the box up above, but we're going to write here anyways in our own writing, that the standard form of a quadratic is y, or actually let's put it in function form, f of x equals ax squared plus bx plus c. Remember, we talked about this being the quadratic term, the linear term, the constant term. In order to be a quadratic function, it at least has to have that term there. All right, the first thing we're going to look for when we graph a quadratic, and you may remember from Algebra 1, is that these quadratics look like these two graphs that we have over here. These are called parabolas, and they have this thing called a vertex where it changes direction. That's what we want to find first to graph it, the vertex. The first part of the vertex we find is the x value. To find it, we take negative b and divide it by 2a. So we take a and b from our standard form and we put them into this little formula here. That'll give us the x value. This actually has some pretty deep meaning where it comes from, and we're going to get to that next week. For right now, we're just going to use it to find the x value. To find the y value, we need to put that back into the function. So using our function notation, we'll say f of negative b over 2a. So to find the y value, you put the x value that you find back into the function. The graph of a quadratic function is called a parabola. The parabola opens up or down. Okay. Later on this year, we're going to talk about how to have a graph of it opening left or right. But in this chapter, we're just talking about up or down. It opens up if a is positive, if a is greater than 0. It opens down if a is negative. If a is greater than 1, it's going to be a narrow graph, because what a ends up doing is stretching the graph. So an a value of 1 is going to end up looking something like this, and an a value of 2 might end up looking something like this, a little bit more narrow. Okay, and as we get bigger, an a value of 5 get very narrow. Okay, if we have an a value that is between 0 and 1, then we'll have a wider graph. So it could be something like this. So a equals 1/2 would be wider. If a is negative, we said it opens down. So any of those graphs that I just drew could be opening downwards if I make it negative as well. So for a equals negative 1/2, for example, it would be wide and opening down. All right, the y-intercept of the graph. Remember, the y-intercept comes from if you put 0 in for x. So if you put 0 in for x, those two terms go away, and our y-intercept is the c value. And we already have the graph of the parent function over here. Well, I guess we don't. It's been shifted. So let's graph the parent function right here. You're going to get really used to this table here because we're going to be using it every time we graph. The parent function is y equals x squared. So basically, all the y values are the x values squared. So if I put in 1, 2, and 3, for example, or 0, 1, 2, and 3, we'd get 0, 1, 4, and 9. Now if I graph those points, I would just get, and I'm just kind of sketching this in here. If I just put in those points, here's 1, 2, 3, and here's 1, 4, and 9, I would only get that right side of the graph. So we need to recognize that we can put negative numbers in here as well. So I'll just put positive, negative out in front of those. Oops. I'll just put positive, negative out in front of these to say, hey, we can put positive and negative 1, 2, and 3 in here. And we'll end up getting the right side of this graph, or the left side of this graph as well. How we're going to do that from now on, though, is we're going to reflect it over this axis of symmetry right there. Okay, I just use AOS to show the axis of symmetry. So the AOS right now is x equals 0, the y-axis. Alright, so here's how we're going to go about graphing these. Okay, well, this first one is like finding all the characteristics. So pretty much everything that you need to do besides actually graphing it. So here's our function right here. Notice right away it's negative and we have a value of 2, so we know that this thing is going to look like this. These terms are just going to shift it. Now they don't tell us exactly how they're going to shift it. It's not like we're going to go one way 8 and one way 7. They kind of work in conjunction to shift the graph, but at least we know that it looks like this graph. It'll look exactly like that graph. If we only had that term right there, it would be at 0, 0, a vertex is 0, 0, and it would be opening down narrower than y equals negative x squared. So we have that idea of what it looks like. It's just going to get shifted because of the 8 and the negative 7. So let's find that vertex first. Negative b over 2a is going to be negative 8 over negative 4, which is 2. So I took the opposite of b over that value doubled. We now then take that value and put it into the function to find out what the y value of the vertex is. Actually, I'm going to come down here right away and say the x value of the vertex is 2. I'm going to come down here and find the y value of the vertex. So we have 2 squared times negative 2. So that's 4 times negative 2, which is negative 8, plus 16 minus 7. That's going to be 1. So the y value of the vertex is 1. Our vertex is 2, 1. So we know that instead of this being at the origin, vertex at the origin, it's going to look exactly like y equals negative 2x squared with that as its vertex. We kind of skipped this part right here. The axis of symmetry gets shifted. It always has the equation x equals whatever the x value of the vertex is, since the vertex is on the axis of symmetry. So x equals 2 is our axis of symmetry. All right, since a is negative, a is less than 0, we know the parabola opens down, and y equals 1 then is the maximum y value, or just the maximum value. I think it's okay if we just leave it like that. Anytime you have a parabola opening down, that's going to be a max value, your y value of the vertex. Anytime you have the parabola opening up, it's going to be a minimum value. Okay, you'll actually have questions on your homework that say, find the minimum and maximum value. Guess what? You're just finding the vertex, and you're naming the y value. This graph is going to be more narrow than the parent function because y equals 2x squared is more narrow than y equals 1x squared because it's getting stretched vertically. And 0, negative 7 is the y-intercept because c is negative 7. So let's talk about the process then for graphing. The first thing you would do is find the vertex. So this is something that we just practiced. Find the vertex using x equals negative b over 2a. Then you find y by substituting x back in. So we've already written this before, but you're finding f of negative b over 2a. The equation of the axis of symmetry is x equals negative b over 2a, just like it was for the x value of the vertex. Now here's where the new kind of part comes in, because what we'll do is plot the vertex. Then what we're going to need to do in order to graph it, we're going to have to multiply all of the parent functions' y values by a. The parent function, remember, is y equals x squared. So you're always going to be using this table. Every single problem, whether you kind of use it, whether you write it down or whether you kind of use it in your head. Okay, to start with, I'd suggest writing it down. And then as you get better, you can just kind of think about what that table looks like and then multiply the y values by a in your head. You're going to graph those points from the vertex. That's huge. You guys are so used to graphing things by going from the origin because that's what you should do when you're just putting values in and getting values back out. Understand that that's not what we're doing. We're not getting values for an XY table like you did in like Algebra 1 by putting a value in for X and then getting a value for Y and then doing that multiple times and then going to a graph and going from the origin. We are using the idea of a parent function that's been shifted. So what we do is we alter this table, that equation and table, by multiplying the y values by a. Then we graph that from the vertex. That's what we found the vertex to begin with. The c value is the y-intercept, so you can use that as one of your points too. You're going to reflect all of these, including that y-intercept, over the axis of symmetry. So if you look at our first problem that we have here, it is that exact problem that we were working with on the front side. So we already know the vertex is 2 positive 1, excuse me. I'm just going to say C example 1. You already took care of that work for that. So we also know that this thing's going to open down, and this is why I leave these axes not on the graph so you can put them wherever you want. I think it's going to make most sense to put the axes kind of high here and somewhat over here, since we're close to the origin. We want this thing, I know this thing's going to be opening down like that somehow. So our vertex is 2, 1, which is right there. There's our vertex. I'm just labeling this on the example. You wouldn't have to label these in all your homework problems. All right, now here's where the parent function comes in. Like I said, every problem you're basically going to be using this table. 0, 0, 1, 1, 2, 4, 9. This is y equals x squared. What we want to now graph is y equals negative 2x squared. Just that guy right there. So x, comma, what that negative 2 does is it affects the y values. So we're going to put negative 2y right there. Our x values stay the same, 0, 1, 2, 3. But now we take all the y values from our parent function and multiply them by negative 2. 0, negative 2, negative 8, and negative 18. Okay? Now, what's important is this gets graphed from the vertex. So in other words, 0, 0 is our vertex. And we plot all our points from there. I think I'm even going to leave another note about that because that's kind of new for us. Graph from the vertex, which is 2, 1. So here we go. From the vertex, we're going to go over 1, down 2. Over 2, down 1, 2, 3, 4, 5, 6, 7, 8. And then down 18, which means I have to go another 10. So 9, 10, 11, 12, 13, 14. We're not going to really fit that on there anyway. So let's just reflect it. If you want to just lightly sketch in your axis symmetry, you don't have to do that. But it kind of helps to go, I'm going to go from here 1, and then I'm going to reflect it over 1 like that. Okay, so I'm going to have a point right there. This point is 2 away from the vertex. I'm going to go 2 away this way. Oh, look what we just found right there. The y-intercept is negative 7. We knew that. We could have plotted that earlier. I'm going to I should have had some of these on here to begin with. 1, 2, 3, 4, 5, just so I can see where I'm going. But everything should work together. So, you know, we just found or reminded ourselves really that, hey, that's our y-intercept because I reflected that over. If we would have landed anywhere else on the y-axis, we would have known that something was wrong. All right, we're ready to just graph this parabola in here. There we go. So now let's focus on the idea that a parabola has a maximum or minimum value. That's not something that we could ever have done with linear functions. So this is kind of an interesting concept. This next problem has to do with revenue. All right, so as you read through this, we've got a number of racers at a racetrack every week, and the owner of the racetrack is charging $35 per racer to race. So the track revenue, let's just start with this. The track revenue that this owner receives is equal to the number of racers, and I know we could calculate it numerically for what he has right now, but we want an expression here, times the cost per race. All right, so right now, I'm going to make this little table over here. Right now, we're going to define our variables in a second. I think this is kind of easier to start like this. Put revenue right here. Right now, we know that if slide this on a little bit. If he just stays with what he's doing, he's going to charge, oops, not $5, $35 per race for 380 racers. So that would give us our revenue. I'm not going to calculate that quite yet. What it says up here before I started writing, I probably should have read the whole problem. The owner estimates that there's going to be 20 more racers per week for every $1 reduction in the price per racer. So every time he reduces the $35 price, so if he were to reduce it to $34, for example, he estimates that he's going to have 20 more racers. So if he does one reduction, he's going to have 20 more racers, which would be 400, but his cost per race he's going to reduce by $1, so it's only 34. So this is $1. Try that again. $1 reduction. If he did lost my $1, two $1 reductions, he'd gain another 20 racers from where he was at, but he'd go down $1. Well, you don't want to do this for every scenario. So now let's use the value X to stand for the number of $1 reductions. So I'll just put an X right here. We'll have X $1 reductions. So what we're doing every time is we're adding 20 for every reduction. So we have 380 as our starting point, but we're going to be adding 20X. And for the cost per race, every time he does a $1 reduction, it obviously goes down by $1. So 35 minus 1X. And if we use these as our X values, we would get these exact values over here using our expression. So that was kind of a way to set up the problem using a few scenarios to help us figure out what X should represent. So let's come up with an equation for revenue. Revenue then is going to equal 380 plus 20X times 35 minus X. Now we want to come up with the maximum value. So let's put this in a standard form by foiling this out here. And I have to open up my calculator here, make this go a little bit faster. So what I'm going to do first, though, is put this into, I'm going to put each of these binomials in a standard form as such. This is not really necessary, but I'm waiting for my calculator to open, so I'm bored. Let's see here. Still waiting. Oops. And what's going to happen is, and we can tell right now, we're going to have negative 20x squared. I'm going to do some of this. Negative 20x squared is our leading term. And then 20 times 35 is 700. So we're going to have 700x. And then negative 380x. And then 38 times 35, still not open. I know I'm missing a zero. I'll add it in at the end. So I got 40, 15, 19, 24, 9, and 11. I'm missing that 1 0, so there it is. So that's going to be our 13,300. And because it's early in the morning, I'm going to make sure that that's true. So what do we take? 35 times 380. Oops. Beautiful. All right, just wanted to make sure. Okay, so now we've got 700 minus 300 that we can simplify here in the middle. So that's going to be positive 420x. No, 320x. Sorry about that. And then plus the 13,300. Now, I'm pretty sure I can get 20 or at least 10 out of all of those. So let's try dividing each of those values by 20. I get 665 here, 32. If I divide it by 10, so if I divide it by 20, it would be 160. And oh, actually, you know what? I'm gonna leave it like this. I'm gonna leave it like this. And we'll just do negative b over 2a here. So x equals negative b over 2a, which is going to be negative 40. Okay, because I'm finding the vertex here. Let's make a little note to ourselves. Find the vertex. So we have negative b over 2a is going to be 8. That is the number of $1 reductions. So he's going to reduce it by $8, in other words. He's going to do 8 $1 reductions. Usually I'd write this with a little bit nicer sentence, but just for time, I'm going to write that. Let's also find what the revenue is going to be by putting 8 back in. So it's going to give us our actual answer. Okay, so if I know that this graph looks something like this. We just found out that that's 8, right? We know that it's crossing the y-axis at 13,300, so obviously this isn't the scale. And I'm looking for this value right there to find out what is that maximum revenue value. So we're going to put that 8 back into the function. Now, there's a couple ways I could do that. I could just literally type that into my calculator here. I want to show you a little bit different way. I'm going to put it into my y equals. So hit y equals. If you miss what I hit, the last button I hit is red on here. I'm going to turn this other stuff off here just because it's kind of messy. And actually, I'm going to clear that out. So in my y equals, I'm going to type my function that I had here. There we go. Okay, so we've got negative 20 x squared. Need the x first. Sorry, my calculator's lagging a little bit here. I got too many things running. Negative 20 x squared. There we go. Plus 320x plus 13,300. Okay, now if I hit graph, I'm probably not going to see anything because it's probably going to look like this, or you might be somewhere else if you grab somebody else's graphing calculator, one of my graph calculators. So we need to get our window to a place that's a little bit more useful. Remember that our y-intercept wasn't until 13,300, so I'm going to go to my window here. Oh, this thing is really slow here. This might not be worth it. We might just have to put this into the calculator. Just type it in, which I'm not going to be able to do anyways because it's locked up. So you would put $8, and I don't have this value on my key. It's the one thing I'm missing. Otherwise, I would just write down what the value is. But you would put $8 back into the function in order to find out what the revenue is as a maximum revenue. It's 8 $1 reductions, and what you get when you put 8 back in would be how much revenue that he he would get. And they're not even really asking that question. They're saying, how can the owner of the go-kart maximize his weekly revenue? Weekly revenue. Well, that simply would be to reduce it by $8. That would maximize the weekly revenue. This might be working now. Let's try this. Hey, it is. Okay, so I'm going to leave, since my vertex I know happens at 8, I'm going to go out about to 20. And my Y minimum, I'm going to leave at, well, I don't know, like, how about 10,000? I'm not going to see the whole graph. I just want to find the vertex. And then the Y maximum is, we don't know. So let's go to, let's say about 20,000 and see what that gives us. We might have to go a little bit higher than that. And let's go by 1,000. Let's see what that looks like. There we see the vertex. Somewhere in there, we don't know exactly where it is. Let's find that vertex using our calculator first. Let's go second and then trace for calculate up there. We want to calculate something on the graph. We want to calculate the maximum. We did show you this the other day, but I think it's good that we do this on the video too. Okay, we'll scroll over here. It's asking for a left bound right there. So we want to go to the left of the vertex. So that's pretty good. Then it'll ask for a right bound. So let's go to the right bound of the vertex, somewhere over here. And then it says guess. I'll just get a little bit closer and hit enter. There's that value 8, as close as it possibly can be. And there we have our revenue, 14,580 is our revenue. So he'd go from the 13,300 that he's at right now. It's currently what he's at. And you'd go up to 14,580. One more way that you could do that. I'm going to quit out of this screen here. Go back to the home screen. If you can get y sub 1 on your graph, that's like using function notation. So no matter what calculator you have, you can always go to this vars button and go to y variables. And go to y variables and go to function number 1. And then hit number 1 for y sub 1. That happened kind of quick. Let me do that again real quick. Variables, over to y variables, and then you want to hit enter on function, and you want to hit enter for y sub 1. Okay. Then you're going to put in parentheses what value you want to put in. We want to put in 8. So this way you don't have to mess with the window in the graph, although it was kind of satisfying to see the vertex of the graph where we thought it would be, and making sure that the window was in the right spot. So we do y sub 1 of 8, and we get that same value, 14,580. So that's how you find the vertex, which in this case is the maximum, on your graphing calculator.